Well, welcome to Lecture 5. This is on the vector Euclidean algorithm, Bezout's theorem, and also linear Diophantine equations. And so I'll begin by just showing you what the vector Euclidean algorithm looks like, all right? And so basically the idea is to just go through calculations similar that we went to last time, but let me just kind of put it up next to here. Here's from Lecture 4. Example 5 in Lecture 4 looks like this, all right? So, like the numbers appearing over here, 2012, so that's, the A and the B, and then 1218, that's the first dividing number and the first remainder, right? And then 84, that's the 8 here and the 4 there. Well, anyway, I'm just saying there's a close correspondence between the numbers if you look at them. And so, of course, you can go and use my brother's website to find these numbers, and then from these numbers you can figure out what to put over here. I want you to understand the algorithm. Well, let's just walk through it here. All right. Excuse me. So I start by putting 2012 as AB. That's my first step. All right. Then 20 divided by 12 gives me a remainder of 8. So I put this 8 down here. And my first dividing number is 12, so I bring that down here. All right. And then, so the 12 goes here just like the B goes there. All right, so I bring B down. And then how do I get 8 from the previous two things? I get 8 from A minus B. So I put A minus B there. Then what? Well then, let's see here. My 8 comes down to here, which is why I bring the A minus B down to there, all right? And then how do we get 4? We get 4 from 12 minus 8, right? So B minus A minus B. Distribute the minus, that gives me A minus B, 2B minus A, all right? And then that was the last non-zero remainder, so that's the GCD actually. So, and then you can see 4 is equal to 2B minus A, right? Which is 2 times 12 minus 20. All right, and that illustrates what's called Bezout's theorem. Bezout's theorem says that there exists x and y integers such that the GCD of A and B is AX plus BY. All right, provided A and B are not both 0. Mostly A and B not both 0, so the GCD makes sense. All right. Now, example 6 was I spent a lot of time on example 6, not in the video, but on my own time. Like, this is an evil example. Like, the numerics in this example are very tedious. But anyway, here it is. So I start with AB, then actually you get a remainder of 231, which comes from subtracting 7 copies of 247 from 1960. So that's why I have A minus 7B. All right. Going back to the lecture, why is there 7 there? It's because 1960 is 247 times 7 plus 231, right? So 1960 minus 7 times 247 is 231. That's why I put A minus 7B there. Now, then this A minus 7B comes down to there, just like the 231 goes down to there. And then the question is, how do I get 16? I get 16 from 247 minus 231, right? So that's B minus A minus 7B, which cleans up to this. All right. Then let's see here. And this continues. Let me not talk through all that. It would be you don't want to listen to it. You can look at it. And continuing the algorithm anyway, we get finally down to here, the last non-zero remainder is 1, because these numbers are coprime. And as such, tracking through these steps, you get 108A minus 857B, which gives me 108 times 1960 plus, or the minus 857 times 247. One of the other very nice things about my brother's website that I mentioned last time is that you notice what he has here for us as well? He has thankfully. Sorry for the glare. Right there, see that? 108 times 1960 plus minus 857 times 247 equals to 1. So he has a integer linear combination that comes from the reverse substituting of these equations, which I would argue is better calculated from this vector Euclidean algorithm I'm sharing with you. All right, but you can, again, check your answers here. You should be aware that these kinds of things are not unique, so it's possible that you, I mean, I think it's plausible you could do it a different way, but I think if you follow the Euclidean algorithm, you'll get the same integer, you'll get the same combination my brother has in the website, so that's useful. Okay, let's look at some more examples. So this is a new example. So example 1, GCD of 142. All right, so I start out by writing 142 is AB. Okay, step 1. Step 2, I bring down the B, and I write the remainder of 100 divided by 42. Well, 100 divided by 42 has a remainder of 16, right? Because 100 minus 2 times 42 is equal to 16. So I have A minus 2 times B, all right? Then we bring the 16 down, and we bring the A minus 2B likewise down. And now we're looking at 42 divided by 16. Well, that has a remainder of 10, right? And how do you get 10? Well, you get 10 from 42 minus 2 times 16. Okay, so that's why we have over here the B minus 2 times that. It just so happens both of these have minus 2. You know, both of these are involving subtracting 2 copies of the thing before, you know. That's just a quirk. All right, and then we bring the 10 down here and put a, why do we put a 6 over here? Because 16 divided by 10 is has a remainder of 6, because 16 minus 10 gives us 6. So again, this 5b minus 2a goes there, because just like the 10 goes there. So just to recap, like, what's going on, any pattern that you see in these numbers must be bared out in the pattern of the letters just the same. So like the letters have to follow the same same pattern, line by line. Let's see here. So as I was saying, 10 divided by 16 has remainder 6. All right. How do you get that 6? You get 6 from 16 minus 10. So what I put here in the 6 slot should be this, the one above, minus that. So A minus 2B minus parentheses minus 2A plus 5B, which is what I put here. And that simplifies to 3A minus 7B. So listen, I'm not trying to say that this algorithm is totally trivial. I don't think it is. It took me a little while to really grasp it. You got to work through it for yourself. Me talking through it isn't going to do it. So, you know, what you got to do is you got to start with one of these and just work line by line until you can get the next line without looking at it. You know, once you can do that, then you understand. But anyway, we continue on until finally we get to 2 as the last non-zero remainder, and you end up with an 8a minus 19b from that. And so that means that we can write 2 as 8 times 100 minus 19 times 42, which I don't think is at all obvious from the start, is it? I would argue not. So apparently 19 times 42 is 798. So 800 minus 798 is 2 here. But, you know, perhaps you should start with practicing an easier example, right? I've been kind of showcasing the, what's the word? The sophistication of the method. Maybe I should start with something simpler, right? Maybe that would be better pedagogy. Let's see here. So 1417 is AB. All right. Whew. Got that. Now we bring the 17 down, just like we bring the B down. And 42 divided by 17 has a remainder of 8. How do we get that 8? We get 42 minus 2 times 17. That's, what is that? 2 times 17 is 34. 42 minus 34 is 8. So there you go. We have A minus 2B. That's how we got the 8. And then 17 divided by 8 is got a remainder of 1, because 17 minus 2 times 8 is 17 minus 16, which is 1. So I bring the A minus 2B down. I bring the 8 down, right? And then I do b minus twice what was up above, all right? And that's the last non-zero remainder, so that's the GCD. GCD of 4217 is minus 2a plus 5b. The 5 is coming from 1 plus minus 2 times minus 2, which is 1 plus 4, which is 5. And here it is, minus 2 times 42 plus 5 times 17 is equal to 1, right? Okay. So this, my friends, is the vector Euclidean algorithm. So it's basically the same song and dance. It's just that we keep track of an A and a B, and that will allow us to see how the GCD is built from an integer linear combination of A and B. And in my experience, this is way, way easier than trying to back substitute the equations like I illustrated at the end of the last lecture. Here's a very silly one. GCD of 20 and 5. Okay, anytime one number is a multiple of the other, the GCD is the smaller number. So like the GCD is 5. So here it is, 20 comma 5, A comma B. What's the next step? Well, it's bring the 5 down and the remainder is 0. So you have B and then A minus 4B. So I don't know, it's kind of cute. It does show you how to get 0 from A and B, right? A minus 4 times B is 0. But anyway, here that is, GCD of 25 is 5 times 0 plus 1 times 5. That's, you can, if you tilt your head and squint, you can see that from the B there. But anyway, so as I was mentioning, shout out to Bill Cook Math website. Very helpful. Where am I? All right, so comment. The if we look at the set ax plus by such that x and y are integers, and these are, you know, positive for a and b not both 0, well, this forms a non-empty subset of the natural numbers, and if we applied the well-ordering principle, that basically gives us a proof of Bezout's theorem, right? That there exists a smallest solution to that, and we'll argue in the next few pages that that smallest solution, in fact, has to be the greatest common divisor. So let's see why. First of all, if C divides A and C divides B, then C divides the GCD of A and B. All right, and that's if and only if, all right? So suppose you have integers A and B not both 0. Suppose C divides A and C divides B. By Bezout's theorem, there exists x and y such that ax plus by is equal to the GCD. Thus, by property 7 from page 4 of lecture 4, we find that C divides ax plus by. Consequently, C divides the GCD. So that's the forward implication. The reverse implication then, suppose C divides the GCD. Then, since the GCD by definition is a common divisor of A and B, we have what? C divides A and C divides B by property 1, all right, of lecture 4. And, well, that's what we wanted. So that's proposition 1. Proposition 2, this is kind of neat because we can also define the greatest common divisor of like multiple numbers. I think my definition was just for 2 numbers, but you could easily extend it to 3 or 4 or 5. So what would the GCD of 3 numbers be? It would be a common divisor of A, B, and C, which is the greatest of all such divisors, right? All such common divisors. It is what you'd think it would be. So here we're going to prove this. The GCD of ABC is the GCD of the GCD of AB and C. All right, this is my proposition 2. So let's let D be the GCD of the GCD AB and C. All right, what does that mean? That means D divides the GCD of AB and D divides C, right? And furthermore, if D prime was also a divisor of GCD AB and C, then we must have that D prime is less than or equal to D, right? Okay, now let's think about it. If D is the GCD of A and B, that means D divides A and D divides B, right? Thus, D divides A, B, and C. Aha, so at least the greatest common divisor of the right-hand side, right, this guy, is a divisor of A, B, and C, all right? So it's in the running for being the GCD of A, B, and C. What do we need to do? We need to prove that D is smaller than any other common divisor of A, B, and C. So I call that other common divisor D prime prime, okay? So suppose D prime prime divides A, B, and C. then d prime prime must divide the GCD of A and B, because it divides both A and B, right, by proposition 1. And thus d prime prime is less than or equal to d. But that's all we needed, right, was that this was smaller than d. Then we find that d is the GCD of A, B, C. And if you can do it once, you can do it again. All right, so you can also prove this, that if you have the GCD of A, B, C, D, you can do the GCD of AB with CD, and then you can do, that is the GCD of the, oh, so much. I think I might have missed a parentheses there. My bad. No, I didn't. Let's see here, GCD. My brain is broken all of a sudden. Sorry, I'm having trouble parsing this. Oh, right. So here I've got it doesn't. So I'm not. I'm just having trouble. This is 3 things, right? 1, 2, 3. So that's the same as proposition 2, right? So basically, if I have this is equal to this, then I can apply proposition 2 and get that. See, because this is the GCD of the GCD of this and that with D. All right, so, okay, anyway, let me, sorry, I'll get with it here. Give me a second. So here's one. The GCD of 20, 30, 5, and 3 is the GCD of the GCD of the GCD of 20, 30, 5, and 3. By this proposition 3, sorry. Which is the GCD, so 20 and 30 have greatest common divisor 10. So the greatest common divisor of 10 and 5, well, that's 5. And what's the greatest common divisor of 5 and 3? It's 1. So the GCD of 20, 30, 5, and 3 is 1. So, yeah. All right, great, lovely. There's also an extended. So I think I've given you some homework problems about those kind of things, but they're, once you understand the trick, it's not too bad. So I do have another example here in another page, so no despair. There's at least another example upcoming. Here's extended Bezout. So suppose you have a1 through an, not all 0, then there exists x1 through xn such that the integer linear combination of the a1 through an is equal to the GCD of the a1 through an, right? And here's a sketch of the proof. You can show that the GCD of a1 through an is the GCD of a1 and a2 with a3 through an, which you can kind of just keep bashing over the head with that relation over and over again until you kind of go down like this. And so each pair, of course, you can apply Bezout's theorem to get the GCD as an integer linear combination of those, and then you can apply you can apply Bezout's theorem again to those, and that'll give you an interlinear combination of that integer linear combination of that and that. And the thing is, if you combine integer linear combinations with integer linear combinations, it gives you yet another integer linear combination. Listen, let me not try to prove this in general, because I don't think it's that interesting to prove in general, and it's better illustrated with an example. So here's an example of what this extended Bezout looks like. So 317, 56. Let's find x, y, z such that the GCD of 317 and 56 is equal to that. All right. So we do the vector Euclidean algorithm. All right. And what we find then is that the GCD of 317 is 1. So the GCD of 317 is 1, which, by the way, is minus 3 times 300 plus 53 times 17. Okay, great. So use the relation. GCD of 317, 56 is the GCD of 317 and 56, but that's the GCD of 1 and 56. You know, calculating the greatest common divisor of 1 in anything is really easy. It's 1. Because the only positive divisor of 1 is 1, so yeah. And so here's the silly Euclidean algorithm for this, which is just 1 is equal to b is basically what you get. So we need 0 copies of 56 is what it is. So 56 times 0 plus 1 times 1. But this 1, right, this 1, you swap out your Bezout result here for the 317 one, and you plug it in there, and you get 56 times 0 plus 1 times minus 3 times 300 plus 53 times 17 equals to 1, which of course is minus 3 times 300 plus 53 times 17 plus 0 times 56 is equal to 1. In other words, my x is, sorry if I was out of screen there, my x is minus 3, my y is 53, and my z is equal to 0. Now, I hope you can see that if this example had turned out differently, like if instead of having a 1 here you had, like, I don't know, 10 or something, then this might have been more interesting in the sense that you would have gotten like 56 times some number plus, you know, some other number plus, you know, some other number times, what was it, 10, if this was 10 instead of 1. So if that 1 was a 10, right, then you have 56 times some number plus 10 times some number equals to the whatever the GCD is with those, you know. And then you would have ended up multiplying your orange one by 10. And so it wouldn't be directly the same numbers that show up here and here that show up in the final answer. It'd be like 10 times it. So generally there'd be some sort of like intermixing of the Bezout for the first time and then the second time. Sorry, this example is not as rich as it might be. So some more examples. So the GCD of 215 and 60. All right, so we can show that, I'll spare you the details, but GCD of 215 is 5, and that's 1 times 200 minus 13 times 15, all right, again by the vector Euclidean algorithm. And the GCD of 5 and 60, well, that's 5, which of course is 1 times 5 plus 0 times 60, by common sense. Okay. So using our relation, GCD of 215 and 60 is the GCD of 200, 15 with 60. But the GCD of 215 is 5, so we have that, which is, again, is just 5. So 5 is 1 times 5 plus 0 times 60. And this 5, right, we go and we basically take the Bezout coefficients from the 215 GCD, and we plugged those right down into, where did it go? Here. If we traded that 5 for this integer linear combination. And so we get that. So 200 times 1 plus 15 times minus 13 plus 6 times 0 is 5. Maybe finally in example 7 we'll have an example where we have all of the x, y, and z coefficients non-zero. Let's see if I managed. Third time's the charms, maybe, right? So next example here, 260, 70. All right, so the GCD of 260 is 20, which is, by the way, 1 times 200 minus 3 times 60. And the GCD of 20 and 70 would be 10, and using my brother's website, of course, minus 3 times 20 plus 1 times 70 gives you 10. Although, I mean, I think we could have guessed this, right? Okay, so let's put it all together. So the GCD of 260, 70 is the GCD of 20 with 70, right, which is 10. So I've got minus 3 times 20, but the 20 I can rewrite as 1 times 200 minus 3 times 60, right? So I take this and I plug it in there. And then I've got plus the 1 times 70. That's the GCD of 260 and 70. And so there it is. Yet another example. So I think I gave you one of those in the homework. I hope this is enough to help you on your way. I should mention that, you know, we could use symmetry, like AB, the greatest common divisor doesn't care which order A, B, and C are in, actually, so you could use that to simplify things a lot, right? If any two of the numbers you're finding the GCD of are coprime, then the GCD is 1, you know? That's no, I didn't do that here, right? I've got the GCD of 30, 7, and 10, right? So if I was going to use the remark above in a smart way, I should just be like, well, this is really the GCD of... Oh, I made it stupid. I mean, I didn't make it stupid. I just made it, you know, I made it more harder. That's not the right way to say it. If I just did the relation directly that we proved, right? Take the GCD of the first two with the second. Well, the GCD of 30 and 7 is clearly 1, right? There's no common factor there whatsoever, except for 1. So, yeah, 1 and 10, which is just 1. So, you know, using the remark to make a problem harder, it's kind of dumb, you know? Sorry about that. The point is, we do have this freedom, and it could be used either in a positive or in, as I have written originally, I would say negative way. Hey. Continuing. Theorem. Let a and b be integers, not both 0, and let d be the GCD of a and b. If c is equal to ax plus by for some x and y integers, well, let me restate that. C is equal to ax plus by for x and y integers if and only if d divides c. Moreover, d is the smallest positive value of ax plus by. This is what I claimed about 10 minutes ago. Now, so now you might, well, anyway, d divides c means that c is a multiple of d, right? And if c is a multiple of d, clearly the value of d must be less than or equal to the magnitude of c. Remember, d is the GCD here, so it's positive. All right, so here's the proof of the theorem. So the proof goes like this. If c is equal to ax plus by, then since d is the GCD of a and b, it divides both a and b, and that follows from c equals to ax plus b that d divides c. Right, because we have that proposition that if you divide both pieces in the sum and you add them together, you divide the whole sum, which in this case is c. All right, so that's the forward implication. The reverse, the converse direction here. Let's suppose d divides c. All right, then that means that c is a multiple of d, and Bezout provides coefficients u and v such that the GCD of ab is au plus bv equals to d. We just multiply that by L, and that gives us C, right? C is LD, which is also ALU plus BLV, which is AX plus BY, where we take X equal to LU and Y equal to LV are integers. Hey, but that's exactly what we wanted to show, so proved. Let's see here. I've been using the, I did introduce coprime in the previous lecture. Let me just define it again because it's an important definition to have stated. Here it is. Integers are relatively prime if the GCD of a and b are 1. If you have n integers, a1 through an, these are relatively prime if the GCD of a1, a2, an is 1. Relatively prime in both contexts is sometimes replaced with coprime, okay? And coprime just sounds better in the third thing here. A1 through an are mutually coprime if any pair of them are coprime, all right? So of course I not equal to j, otherwise it's just silly, right? So notice that mutually coprime implies coprime because if you have the GCD of any pair of them being 1, then it implies the GCD of all of them is 1, right? However, if the GCD of all of them is 1, it doesn't imply that the GCD of any pair of them is 1. Here's an example. 6, 10, 15 are coprime, all right? But 6, 10, 6, 15, and 10, 15 have, you know, common GCDs of 2, 3, and 5 respective. So not even one pair of them is mutually coprime, right? So that's yeah. Corollary. If a and b are relatively prime excuse me, I keep saying it wrong. Integers a and b are relatively prime if and only if there exist integers x and y such that ax plus by equals to 1. So as a point of order, when I'm trying to prove something about coprime integers, this is the first thing I think about. I think about the fact that I can build this equation like that to describe them. Anyway, so here's the proof. If the GCD of a and b is 1, then by Bezout's theorem, we can have ax plus by equals to 1 for some x, y, and z. Conversely, okay, so that's the forward direction. Conversely, if there exist x and y such that ax plus by equal to 1, then by the theorem, that means that the GCD divides 1. But the only way you can have a divisor of 1 in a positive number is if it is 1. So there you have it. Moving along here. So next up, corollary 2. If the GCD of a and b is d, then if you multiply a by m and b by m, you get the GCD of the multiplied ones by just md. All right. And also, the GCD of a over d and b over d is 1. So if your numbers aren't already coprime, if you divide them by their greatest common divisor, if you divide both of them by the greatest common divisor, then they give you a coprime pair. It's kind of neat. So let me get my cover paper. Where did I put my cover paper? I know I had a cover paper here somewhere. There it is. All right. So suppose the GCD is d. Let m be a natural number, and notice that the GCD of MA, MB is the smallest positive value of MAX plus MBY. And so that's m times AX plus BY. And since D is the smallest value of AX plus BY, it follows that the GCD of MA, MB is MD. Now, there are other ways you could prove that, so if you don't like the way I proved it, prove it a different way. All right, but now since D divides A and D divides B, that means both A and D, A over D and B over D are integers. And since D is equal to AX plus BY, that gives me that 1 equals, so I divide this by D. Sorry, dividing by D gives me 1 is equal to D over A, that's supposed to be an A over D times X plus B over D times Y. These are integers, right? Equal to 1. But hey, if there's integer linear combinations equal to 1, that means that the GCD of A over D and B over D is 1, because we had that result. They're coprime if and only if there's a integer linear combination equal to 1. So there you have it. Here's an example of that. Suppose we look at the greatest common divisor of 780 and 637. I don't think it's altogether obvious, but it's 13, all right? And 780 over 13 is 60, and 637 over 13 is 49. And so the GCD of 60 and 49 is 1. So that's kind of neat to see that corollary in action, right? So let me ask some questions now. So coprime, the property of coprime is important. Let's see how not having coprime affects us. Number 1, if we have A divides C and B divides C, is it the case that AB divides C? Well, in fact, it's not the case, because check it out. We could have like 9 divides 27 and 9 divides 27. Okay, so I just took A and B to be equal. But certainly 9 times 9 is 81. 81 does not divide 27, so nope. The answer is nope. Question number 2. If A divides B and B times C, then does A divide C? Well, let's see here. I said 10 divides 100, all right? And I can think of 100 as 50 times 12, right? Does 12, listen to me, 50 times 2, 100 is 50 times 12, good job, dummy. So 100 is 50 times 2. Does 10 divide 2? No, it does not. So no, these questions are definitely answered by no, unless, let's see, they do sometimes hold. right? Like 3 divides 42, and 7 divides 42, and when I multiply 3 times 7, I get 21, and that divides 42, right? So if I put a equals to 3 and b equals to 7, my question number 1 has a positive answer. And for question number 2, if I put, I look at 5 divides 70, and I look at 70 as 7 times 10, I do get 5 divides 10, right? Here I'm thinking of a and b as 5 and 7 in question 2. So maybe it jumps out at you, 3 and 7 and 5 and 7, these are coprime pairs, right? So apparently that's the thing that we need. We need coprime for questions 1 and 2 to have affirmative answers. So here's the corollary 3. That's not a proof, obviously, right, guys? That's just some evidence. We'll prove it below. Let a and b be coprime. Then if a divides c and b divides c, ab divides c. Number 1. Number 2, if a divides bc, right, then it must be that a divides c. See, because basically the idea is a does not divide b when a and b are coprime. So like it forces the a to must be dividing into the c. That's the way I think about it anyway. So here's the proof. Proof number 1. So GCD of a and b is 1. So by Bezout we can have ax plus by equals 1. But we're also assuming that a divides c and b divides c, right? Which means that c is a multiple of a and c is a multiple of b. And so we can write c as equal to c times 1, which we can rewrite as ax plus by, which is cax times cby. And then we'll replace c with ja and kb, respectively, right? So see that kb is this kb, right, which was formerly this c, and this ja was formerly this c. So we got to make a smart substitution so we get an a times a b in both of the terms being added. In so doing, we can factor out ab. We got, oh, wait a minute, so c is a multiple of ab, which is to say that ab divides c. All right, so that's the proof of 1. Proof of 2, so suppose a divides bc, a and b are relatively prime. There exists j such that bc such that bc is a multiple of a, right? So bc is equal to ja, and so then I can look at c is equal to cax plus cby again, but this time my cb becomes ja, and I can factor out an a, and so I get c is a multiple of a, which is to say a divides c. So there's the proof of 2. So that wasn't too bad. These we will use in future analysis of primes and such. So what's a prime? I don't know. We talked a little bit about that, but we'll talk more. About 2 lectures from now, I guess. But. Okay, so up next we can talk about least common multiple. So what's the least common multiple? Well, it is what it sounds like, isn't it? If a and b are integers not both 0, then the LCM of a and b we'll call L. It's going to be the natural number such that L is a multiple of both a and b, which is to say that a divides L and b divides L, right? So L is a multiple of both a and b. And if c is positive and c is a multiple of both a and b, it must be that c is greater than or equal to L. So it is, like it sounds, it is the least of all common multiples of a and b. There's a really neat theorem that relates the GCD and the LCM. And here it is. If we have a and b integers, positive integers, with d is equal to the GCD of ab and L is equal to the LCM of ab, then the product of the GCD and the LCM is just the product of a and b. So that's pretty cool. So here's the proof. So if we have a, so let d be the, we're going to let d be the GCD of a and b. And notice that since d divides a and d divides b, that means that a over d and b over d are both positive integers. So then we can look at ab over d, and so that gives us, like, you know, dj dk over d, but then the d's cancel and we get djk. And what we're going to argue is that djk is actually L. So we're going to argue that the least common multiple of a and b is this d times j times k. So first of all, notice that it is a common multiple, because L is djk, which is d times a over d times k, which is ka, and it's also d times j times b over d, which is jb. So it's a multiple of a and b. That's the first thing. Then the second thing is that if we have another multiple, right, positive multiple c, which is a multiple of a and b, right, a divides c and b divides c, that means that c is equal to ma and c is equal to nb for some m and n. And of course, by Bezout's theorem, we still know that ax plus by is equal to d. So let's look at the ratio of, sometimes when you're trying to find an inequality between two numbers, it's useful to look at a ratio of those numbers. It will be here. So I'm going to scooch it up here a bit. If we look at c over L, which is c over djk, then that is cd over dj dk. But remember, dj is a and dk is b. So we've got cd over ab. But also remember that d is by Bezout, ax plus by. So then, by algebra, we've got c over b times x plus c over a times y, because we can cancel the a's on the first term and we can cancel the b's on the second term, leaving us this and that. But remember, c is also equal to mb, and mb and nb, m as in mummy, n as in nenu nenu. A soon lost reference, an already lost reference, I should mention. Anyway, so the b's cancel in both, and you're left with, what are you left with? You're left with mx plus ny. So what you got is that c is equal to mx plus ny times L, which is to say that there's a positive integer times L, which gives you c. Clearly that is greater than or equal to L, right? Because the smallest this could conceivably be would be 1. Because remember, both L and C are positive here. So, yeah, there you go. Here's an example. The GCD of 780 and 637 is 13. The LCM of 780 and 637 is 780 times 637 divided by 13, which is obviously 38,220. Huh, that's kind of funny. And, why is that? Well, if we go back to elementary school math, 780 is 13 times 60, and 637 is 13 times 49, right? So I've got a common 13 in both places, so I don't need two copies of it. I just need one copy of 13, one copy of 49, one copy of 60 to get me both a 780 and a 637, to get a multiple of 780 and 637, which is smallest as possible. So you can, pick one of each factor that appears, or I don't know how to say it clearly. You guys use trees and vector trees and all that good stuff, whatever. But or we could just calculate the GCD and take the multiple of the numbers divided by the GCD, and it'll give us the LCM, which is kind of neat. Because finding the factorizations of numbers is harder, right? It is harder. So, like I said, as a child I calculated LCM using prime factors, but this theorem allows for a very different method. Here's another one. GCD of 20 and 110 is 10. So the LCM of 20 and 110 is 20 times 110 over 10, which is 220. Which of course we could also figure out from just like basic, factoring. 20 is 20, 20 is 2 times 10, 110 is 11 times 10, so like I need a 2, I need a 10, I need 11 to get my LCM, but there it is. Finally, last up here for this lecture is the problem of linear Diophantine equations. And I probably should mention my secret word before I forget. What is the secret word for today? The secret word for today is calculator. Secret word for lecture, what lecture are we on? Lecture 5? Lecture 5. Calculator. All right. So this is, Diophantine is in reference to Diophantus of Alexandria. Did this stuff about 300 AD. Also Brahmagupta, which I have mispronounced, I'm sure. 628 AD, India, also did a lot of these things. So the problem here was to find integer solutions of ax plus by equals to c. And the reason I'm talking about that in this lecture is basically everything we've done with the GCD and Bezout's theorem. It naturally leads to a clear and concrete solution of this problem. So the solution is this. If we have ax plus by equals to c, it must be that c is a multiple of the GCD of a and b, which means that if d does not divide c, there's no solution. Okay, but good news, when c is a solution, when c is a multiple of d, the solutions have the form x equals to x naught plus bn over d, and y equals to y naught minus an over d, where x naught and y naught is any particular solution, and d is the GCD. Now, we know how to find a particular solution using the, for example, Euclidean algorithm, essentially. So let's see how that goes. All right. Well, I guess first I owe you a proof. So here's the proof. First of all, we can apply the theorem from page 6 to see that ax plus by equals to c can only have a solution if d divides c. So let's let d be the GCD of a and b. Then by Bezout's theorem, there exists u and v for which au plus bv equals to d. And then what? Well, if d divides c, then c is equal to dj for some j, right? And so we can multiply this equation here by aju plus bjv equal to jd equals to c, and voila, we've found a particular solution. By the way, this is the same way we'll do it in examples. We can do the vector, vector Euclidean algorithm to get us the linear combination that gives us the GCD, and then multiply by like whatever j needs to be to get to c. I have an example, so we'll see it, but just saying the proof and how we'll work the problem the same way, okay? Then what's in purple? We need to find, I'm going to show you that any solution has to have the form given in the theorem, okay? So let x and y be any solution of ax plus by equal to c. Then since ax plus by is equal to ax naught plus by naught, which is, of course, these are both equal to c, so they're equal. We find that a times x minus x naught is equal to minus b times y minus y naught, right? So divide by d, we get a over d is equal to minus b over d times, x minus x naught and y minus y naught respectively. So if b is not equal to 0, then b over d is coprime to a over d. As we know, we proved earlier in this lecture, the GCD of a over d and b over d is 1. So what do you got? Well, you've got b over d divides the right-hand side. That's just obvious, right? And if it divides the right-hand side, it must also divide the left-hand side, right? So b over d divides that. But the thing is, b over d and a over d are coprime, which means if b over d divides this too, it has to divide that. That's the only choice. And so b over d divides x minus x naught. But what does that mean? That means that there exists an n such that x minus x naught is a multiple of b over d. All right? So that gives us x is equal to x naught plus bn over d, which was part of the theorem. And then if you just plug this in, if you solve solve this equation up here, for example. Let's see where to solve which one. Oh, where to solve? If I solve this equation, for example, I mean, there's any number of ones you could pick on, but if we just take this and, so let's see, I'll call that star. So I solved star for y. okay? And that gives us y naught plus a over b times x minus x naught minus x. So then we plug in the solution over here into there, and the x naughts cancel, and we're left with the b's cancel, and then we're left with y is equal to y naught minus an over d, which is pretty cool. And it's actually, like, this proof I have found mystifying before when I hadn't worked through this section. So this is mostly from Jones and Jones. Oh, rats. I don't. Oh yeah, here it is. So, you know, this book here, and I mean we're working through chapter 1 here. So I've just tried to, you know, not study the whole chapter and just look at this theorem, and it seemed mystical before, but actually it's very understandable if you've worked your way up to this point. And anyway, here's some examples. So solve. Let's see here. Solve 10x plus 2y equals to 4 over z. All right. So the GCD of 10 and 2 is 2. 2 divides 4. So there exist solutions. In fact, you can easily guess the solution of 2 and minus 8 here, right? Because 20 minus 16 is 10 times 2 minus 2 times 8, which is 4. So that's good. And then if we use the theorem, we have x naught plus b over n. Y naught is minus an over d, which is 2 plus 2n over 2 minus 8 minus 10n over 2. And of course these have to simplify to numbers. We get 2 plus n and minus 8 minus 5n. Quick check on our work. Try to plug it into the equation, see if it works. 10 times 2 plus n plus 2 times minus 8 minus 5n. So we get that 20 minus 16, which gives us 4, and these give us 10 times n, which is 10n. 2 times minus 5n, which is minus 10n. Those cancel to give me back 0, and I think equals to 0. Sad. 4. It equals to 4. Anyway, so here's another example. That one wasn't too bad. 3x plus 8y equals to 13. Well, in this case, 3 and 8 are what? They are relatively prime, right? They're coprime. And so if that's the case, then surely they divide 13, right? If the coefficients are relatively prime, you can solve it. All right, that's just the case. And so this time, rather than guessing, I'm going to actually sort through the vector Euclidean algorithm. All right. So 8, 3 is BA. I made it AB, and that led to great confusion because I've used A and B in this theorem in a very specific way as the coefficients of x and y respective. So if I flip the meaning of A and B in this, it's not good. So that's why I'm putting BA instead of AB here. So, and that's also why there's whiteout and messy writing. So 8, 3 is BA, then I bring my 3 down. 8 divided by 3 has a remainder of 2. To get that, I do 8 minus 2 times 3, so B minus 2A. And then 2 divided by 3 has a remainder of 1. How do I get that? I get 3 minus 2 is 1. So A minus 2 times, A minus, rather, B minus 2A, right? It's going to give me 1 is equal to minus B plus 3 times A. All right. And so rewriting that a bit, we've got, that's not what we want yet, right? We're trying to solve equal to 13. So, but that's almost right. I got 3 times 3 plus 8 times minus 1 equals to 1, right? So then I multiply by 13. 3 times 13 is 39. 3 times, excuse me, multiply by 3, listen to me. Sorry. Multiply by 13. Multiply by 13, 3 times 13 is 39. Minus 1 times 13 is minus 13. And there we go. 3 times that plus 8 times that is 13. That is a particular solution. X naught equals to 39, y naught equals to minus 13. So noting that the GCD of 3 and 8 is 1, we have that d is 1. So we get 39 plus 8 times n minus 13 minus 3 times n. And so our solution set is exactly this, right? So since we have a minute, not much though, let me just add one more example here and then we'll be done for this lecture. And example 12. So what if you were to solve, 3x plus 6y equals to, oh, I don't know, 11, right? Then if we were looking for integer solutions, we'd be out of luck, right? So this, the GCD of 3 and 6 is 3, and clearly 3 does not divide 11. So there does not exist integer solutions. Of 3x plus 6y equals to 11. However, I would point out that there are infinitely many rational solutions to this. See, because all I have to do is solve for y, right? What would y be equal to? Y would be equal to 11 minus 3x divided by 6, right? And so that is for any x in the rational numbers. See, so not having solutions, it's just a consequence of being fussy and wanting integer solutions. If we free ourselves from integers and we allow ourselves rational solutions, well, then these problems are all solvable. And not only do they have solutions, they always have infinitely many solutions, right? So Diophantine or equations are very demanding. Finding whole number answers to algebra equations is very, very difficult in general. Finding rational answers to algebra equations, a little bit easier. Finding real answers, easier still. Finding complex answers, piece of cake. So anyway, I will stop there. Next time we look at an analog of the Euclidean algorithm for polynomials, and there we'll see how to rationalize some fractions involving cube roots and so forth that you would be stumped if you just tried to use high school algebra. So perhaps you'll find that interesting. Anyway, up next time. Thanks, guys.